we're going to focus now on the terrestrial coordinate systems, and not all of them, but the ones that starts from the go back. This is the let me get a color here. Let me get red. Okay, we start from a topocentric system that is local astronomical. That's the system where observations are made, and moving all the way towards the geocentric systems. All these three systems, they have the origin at the center of mass of the Earth. And the good thing is that when we arrive at the system of apparent places, we know that this system is the same as the system of true right ascension, so that's a connection to the celestial system. Local astronomical system, or LA. First of all, something that is important to emphasize: the word astronomical. This system, we refer to it as a system where observations are made, terrestrial observations are made. Now, a long time ago, we just dealt with mostly astronomical observations, and that's why we have the name. And of course, now we have, there are other types of observations that are also made: zenith and azimuth, distance. They may not be done for astronomical purposes, but they're all in the system of local astronomical. Okay, so just as important. We'll be focusing more in the sense of terrestrial observations in terms of directions. This is the elevation angle, and we have also the so that's a vertical angle, and the azimuth, so horizontal angle. We can also deal with distance. So if we have, for example, a target in here, of course we have the zenith, and we have the azimuth. How this local astronomical system is defined: the origin is the observation point. Gravity crosses through the point, going through towards the nadir. The zenith, the direction of the zenith defines the primary pole. That's the z-axis. The primary axis points towards the north, and this is the x-axis, in such a way that the plane that contains z and x forms the astronomical meridian of point P. The y-axis is defined in such a way that this local astronomical system is left-handed, and it points towards the east. And the direction, the plane that contains x and L form the local horizon. Okay, the plane XL. We have here all the definitions that I just mentioned, and here is how we define the coordinates, the local topocentric components. Here to the observations. So observations is the vertical angle or elevation angle. This is basically related to the zenith, and the azimuth, and we're going to refer to this as astronomical azimuth, even though it might have not been measured astronomically. It may be just a azimuth that we have computed, or it might have a azimuth that we define with the gyroscope, but we refer to as astronomical azimuth because it's a local astronomical system, to distinguish the other type of azimuths that we're going to see later on. So the x component, then it can be computed based on the trigonometric relations with respect to the vertical angle and the azimuth, the same as the y and the z-axis. They're all trigonometric functions. What we have here basically is the unit vector. Okay, so that's the direction. If we want to have a coordinate, okay, in this LA system, we would have to have a distance. Okay, you would have to have a distance be measured, and that distance would then be multiplied to each one of the components. Okay, and then now we have a full-blown vector with scale. Now we are going to be mostly focusing on the unity vectors, because they're going to be defining rotations, how we relate the local astronomical with the next one. And the next one is the most important coordinate system, the conventional terrestrial system. It is most important because it is the closest practical approximation to a geocentric natural system, and it is basically the system that satellites, or the artificial satellites, they orbit around. The location, by definition, is at the center of mass of the Earth. Again, this is a definition. We're talking about a system. In practice, it's not going to happen. The origin is going to be very close by a few centimeters of the center of mass. And here we have the definitions. So this slide here that comes from Vanecek and Krakowski. Here's the center of the conventional terrestrial system, and what we have is the direction towards the z-axis. The z-axis, this is the primary axis. It points towards the CIO. This is a conventional international origin. Now we're going to see these also called as the conventional, as the CTP, conventional terrestrial pole, and this is a conventional pole. Okay, so CIO is how it used to be called. The CTP, because of the new more modern systems, they use a different epoch. But that's important that it rotates towards a conventional pole. And the x-axis, this is the primary axis, points towards Greenwich, but it points towards a mean or conventional Greenwich. Okay, and we have the y-axis being defined in such a way that the system is right-handed. And what we have is that the plane that contains the x and z, the z and x axis, they form the Greenwich astronomical meridian, and the horizontal plane that contains x and y, it defines basically the equator. And so if we have an observation, this observation point in the local astronomical system, the projection of the nadir when it intercepts the equator, it will define then the longitude, and we call this longitude the astronomical longitude, and defines the latitude. This is the astronomical latitude. So, how do we relate conventional terrestrial with the local astronomical? And again, we are talking about unity vectors, and but this relationship can be applied also for vectors with a scale. So first of all, we have to apply a reflection matrix P. If you recall, this matrix is just change the polarity of the y-axis. Then we have two rotations. One rotation that is the argument is the astronomical latitude. The other is the astronomical longitude. So if you develop this expression, this is the full-blown rotation matrix that we have. And the inverse transformation, it's relatively simple because it's the opposite side. So instead of now we want to go from the CT to the LA, so we start applying a rotation RT. So this is the inverse of this, and transpose, then rotation R2, okay, transpose, then the P2 matrix, which transpose is the same thing. Now, by the properties of rotation matrices, we can write these in this way here. So it's the same thing. So it's a simple relationship, and it's a very important. So we can then relate the observations that we take, the terrestrial observation that we take in the local astronomical into the conventional terrestrial system. So now another system that is very important is the instantaneous terrestrial system. So this terrestrial system is well, before that, just so that you know, the conventional terrestrial system, just to make sure that we understand this is system, the big thing for us to have realizations of this system, because it's geocentric, and historically it was never possible until we came the satellite age, and so we start to have satellite-based observations to define coordinate systems. The NAD 83, the one we use here in Canada, in North America in general, in Canada in particular, was defined as geocentric, but we know it's not. The geocenter is offset by about 2 meters. There are other systems, other coordinate systems that define. The most important ones right now are the ITRFs. The ITRFs are, well, that's the frame. They are materialization of the ITRS, Terrestrial Reference System, and there is a number of those. Okay, so basically we can think that today we work with systems that are very close to the conventional terrestrial system. Instantaneous terrestrial system, the usefulness of this system is basically to study polar wobble. Okay, how much the instantaneous spin axis differs from a conventional one. So this is the z-axis of the conventional terrestrial system. This is conventional, it's attached to an epoch. This is the instantaneous axis. Okay, and you probably remember from Geodesy 1, we have the a conventional pole, and the instantaneous is going to move around. Okay, and how they relate, they basically relate by means of these two elements. These are the components of the polar wobble, or the components of the Earth rotation, and so they call Earth rotation parameters XP and YP, and they are determined by means of observations. Space techniques today mostly, previously was more the astronomical observations, and they're provided by the International Earth Rotation Service. Here is how a unity vector towards a target relates in the conventional terrestrial system, relates to the unit target international in the well, unity vector in the CT relates to the unity vector in the IT. We have the two rotation matrices. There is no polarity because both are right-handed, and the elements are the Earth rotation parameters. We can develop the whole these two rotation matrices and arrive at one expression like that. This matrix is known as the wobble matrix. Okay, and it's usually represented by the letter W. And we can just use the elements X, P, and YP expressed in radians. An inverse transformation, we just apply the properties of the rotation matrices. The final system, and now we are touching the celestial systems, the system of apparent places, AP, apparent places. And this system, it's also very important for us because it has to do with the length of day. So length of day, we call that just LOD. The length of day will tell us how much fast or slow the Earth is rotating. So and it's something conceptually very simple. What we have to think of now is that the primary axis is fixed in space. It points toward the vernal equinox. Now, the system of apparent places, both axes, Z, the Z-axis and the Z-axis of the IT, both AP and IT systems, they coincide. So the only difference in this system now is the rotation of the Earth, because the IT system is fixed with respect to the Earth. So which means that the IT is going to be moving, going all around here until it crosses the X of the AP. So there are some angles that are defined, and this is known as guessed. Greenwich apparent sidereal time, which is the angular distance between the primary axis of the instantaneous terrestrial and the primary axis of the apparent places. And if we have a observer observing a star, okay, or a target, then what we have here is basically the right ascension, okay, the same right ascension as defined before. If you define this direction as the local meridian of the observer, instantaneous meridian, because this is also rotating, what happens is that we have here the longitude, and we are going to have this angle, that is the hour angle, and the angular distance between the instantaneous local meridian and the fixed axis that points toward the vernal equinox is the local astronomical, the local apparent sidereal time. So that's important. So the relationship between these two systems, the system of apparent places and the instantaneous terrestrial, is just one rotation, and the argument is guessed. Okay, so that's why people call this matrix as the guessed matrix, and they refer as G in literature. The thing is that recently it was changed. We don't use the guessed anymore. That is a better way, or more accurate way, to compute, to relate two systems, and this is done by means of the Earth orientation angle. Now the idea is very similar to the guessed, but the computation is done by this expression that came from the IAU. IAU is International Astronomical Union. They came with resolutions. And I'm showing this. I mean, we don't need to bother to compute, but if you know the Julian date of the observation, we can basically evaluate the ERA. And so, which means that the expression now is the same, very similar. The difference now is that the argument for the rotation is not guessed anymore, but it's ERA. So we have gone all the way now to relate the celestial system to the conventional terrestrial system, and this is done by means of all these matrices that we have discussed. If you have a direction in the conventional celestial, we can go all the way to the conventional terrestrial by means of precession notation, guessed, the G matrix, and W. G actually is referred now as the Earth rotation matrix, not as the guessed matrix. And if for the inverse, okay, and if we're dealing with vectors, Okay, we also use the same rotations: precession rotation, G, the Earth rotation matrix, and oval matrix. Now, it is very important because the orbits of a satellite are dealt with, are determined in the conventional celestial system, and the orbits of points on the Earth are, the positions of points of the Earth are defined in the conventional terrestrial system.